Hi, it's Ilya, and today I'm going to talk about the multimodality problem in robotics. In simple words, multimodality is the case when you want to predict the next best action for the robot, but there are multiple equally good actions, and your model, your policy somehow should choose one of them. And I think it's a very interesting topic because in the classic machine learning, for example, in classic regression problems in machine learning, you rarely deal with multimodality problem. But in robotics, it's happened all the time. So probably one other area where it's always pretty common is Gen AI. This is why robotics models often use some Gen AI ideas and Gen AI approaches. So in this video, I will try to give you very high-level rationale, high-level explanation of why multimodality is the problem and how different policies, different approaches deal with this problem. And I will try to explain everything in like very, very simple terms. But still, you probably need some high-level understanding of machine learning, and you need to be able to understand Python code to follow everything that I'm talking about today. In the beginning of the video, I will talk about definitions a bit more and also introduce the toy problem that I will use through the whole video. And then I will go to the main part and discuss different approaches to solve multimodality, starting from the simple one like change in the loss for your model training up to more complex approaches such as diffusion and flow matching. So let's begin. I created this Python notebook that has demonstrations and different illustration and code for everything I will be talking about. And this notebook available both on my GitHub, and I also uploaded it to Kaggle. So if you want to just play with it online, just go to Kaggle. If you want to download it, probably easier to go to GitHub and run it locally. And yeah, you can either follow it while watching the video, or you can watch the video first and then play with notebook, try to experiment with changing different parameters and so on and so forth to better understand what I was talking about. So yeah, let's just go forward. So this notebook starts from a lot of imports and helper functions. I will not talk about them because they're mostly here for some illustration purposes. They generate some nice pictures later in the notebook. So just run them, but we'll skip them. And yeah, so let's start from the definitions. Let's talk about multimodality and what it is. The interesting thing is that the word multimodality has two different meanings in the context of machine learning, AI, and like even in context of robotics. They're, let's say, not applicable for this particular video definition is about ability of the model using different modalities. So I think it's kind of more common use of this word. And let's say when you use some state-of-the-art LLMs, let's say ChatGPT, this model can accept text, audio, and images as input, and it also can generate text, audio, and images. And these like three types of data called three different modalities of data, and this model is called multimodality model. So it's not the definition that we will use for this video. It's a different one. So in this video, when I say multimodality, I mean that we deal with some target distribution that has multiple modes. Let's show on the simple example what it means. So most of the, let's say, popular distributions that we usually use in different problems in the like real life have only one mode. So mode is this top point, this like peak of the distribution. So if you plot this bell curve of normal distribution, it has only one peak. And student distribution that used in a lot in A/B testing also has one peak. Log normal distribution has one peak, and so on and so forth. There can be like many different distributions that you can come up with that have only one peak. And it's very common in classic machine learning in regression problems to deal with distributions like this, because we assume that for some set of inputs, the output has one correct answer, one correct value, and there is always some noise around this value. So more or less distribution of the targets in your training data look like this for each particular combination of the input variables. And a lot of approaches in classic machine learning kind of dealing with this type of target distributions. In reality, there can be a lot of cases when distribution has multiple modes. These modes can be equal, there can be some dominating modes, there can be more than 2, there can be like 3, 4, 5 different number of modes. Sometimes these modes are far from each other and like all the probabilities are mostly concentrated in these modes, or like here they're also kind of pretty far. Sometimes they're located pretty close, and actually like even being in between modes is not so bad because there's pretty high probability in this point, and so on. So it can look very differently, but yeah, the idea is that in this case you don't have like one main value around which everything is distributed. You have like at least 2 of them, or sometimes even more. And this is very, very common in robotics. So think about it, for example, when your robot is some autonomous car and there is an obstacle in front of this car, your car can go to the left and can go to the right to avoid this obstacle. And in many circumstances, both of them are kind of correct actions. If we are thinking about the humanoid robot and this robot wants to go forward, it can start from either leg. So it can start from the left or right leg. And again, in most of the cases, they're equally correct actions. Even so, they're actually very different if you think about the distribution of the, let's say, motors positions that we want to predict. Another case is if you have a robotic arm and you want to grab some object, you can grab this object from the right, from the left, from top, from the front, and so on. So there are many, many different ways. Again, some of them can be better, some of them can be worse, but the idea is that there are many different options to complete the same task. And if you look at the distribution of the, let's say, motor positions of the robot, or like correct motor positions of the robot that we want to predict, then these distributions will look like these charts here. They will have multiple modes, multiple peaks, and each of these peaks corresponds to one correct action. So yeah, so and this is the problem, because many classical machine learning regression approaches are not supposed to deal with this type of distribution. And yeah, to visualize it more and to have like some example to deal with through this notebook, I created the very, very simple problem. So I tried to create something that looks like real problem but is simplified as much as possible, and I make a small visualization for this. So let's assume that the robot that we're trying to control is simply this green square over here, and this robot is constantly moving forward. So there is some speed that we cannot control, so it's like constantly moving forward. The only thing that we can control for this robot is the horizontal position. And yeah, so we have like only one dimension that can be controlled, and only one dimension that represents the position of the robot. From time to time, there is a red square obstacle that appears in front of the robot. And for simplicity, to reduce the number of variables, instead of using the coordinates of obstacle and coordinate of the robot, I'm switching to the coordinate system attached to the obstacle. So I assume that obstacle always appears in the middle, and the coordinate of obstacle is always 0. And then the coordinate of the robot is always relative to the obstacle. So if the coordinate of the robot is 0, it means that we are exactly in front of the obstacle. If it's positive, then we are slightly to the right. If it's negative, we are slightly to the left. And then I also assume that our object is moving very fast, and we have basically only one chance to avoid this obstacle. So we cannot self-correct ourselves and so on. For the next moment, we need to predict what should be the coordinate of the robot to avoid the collision. And this is our action. So our action is simply the prediction of where we should be in the, let's say, next moment to avoid the collision. If our action is higher than 1, so it means we don't intersect, don't collide with the obstacle, then it's success. If it's lower than -1, it means we go to the left and also avoid the collision. It's also success. If our action is intersecting or colliding with the obstacle, it is fail. And also, I assume that we have like enough acceleration to jump to any position from any other position. So there are actually no limits. Even if we are located initially on the right, we can jump to the left and vice versa. So you can see that actually correct solution that leads us to success doesn't even depend on the initial position of the robot. There are infinite amount of actions that will lead us to success. So it's a very simple problem. It's extremely straightforward. But again, we are not trying to solve this problem right now. We just want to generate some data using this problem and see how different models trained on this data actually behave. Because in reality, when you train the real robots, your multimodality cases are much more complicated. You cannot visualize them like this. You don't really know when you have multimodality, when you don't have. You cannot predict all these cases, and you cannot really like solve it yourself. So again, this is extremely simple example that can be solved without any machine learning, obviously. But I want to demonstrate on this example how machine learning policies solve it and how they deal with it. So to demonstrate it, I create the data set using like this logic. If our robot initial position is in the middle, then with 50% probability we go to the right, with 50% we go to the left. If initial position is on the right, then the probability of going to the right increases. And if we already kind of avoid an obstacle without any changes, then we will stay on the same side. And then when we move to the left, the probability to go to the left increases and eventually reaches 100%. And if you're already on the left, we will, with 100% probability, go to the left. So this is the logical generation of data that kind of represent some common sense, how probably people will operate this robot if we give them this opportunity. So I generate two data sets. One contains 10,000 samples for training, another contains 1,000 samples for testing. This data set is just pandas data frame with two columns. The first column, named S, represent the state of the robot, the current initial state, randomly distributed. The second one is X is X coordinate, or like action that we are predicting. And this is where our robot will jump in the next moment to avoid the obstacles. So again, it's just extremely simple, one input, one output that we will want to predict. And let's plot these distributions. I prepared this chart and I will use it across multiple examples. So let me talk a little bit about it. So in the left top corner, you can see the distribution of all the data points in the data frame. So each blue dot is just like one line in our data frame. And on the horizontal axis, you see state, the initial position of the robot. On the vertical axis, you can see the X, or action, of the robot. You can see that all of the actions that I generated are correct. So the action is never between -1 and 1. So all the actions lead to success. We have very clean and good data set. And you also can see that density of the points on this like positive side, on the like going to the right, increases when we move our initial position, our state, to the right. So as I said, in the middle there is like 50-50 probability to go to the left and to the right. But when we are already a bit to the right, there will be much higher probability to kind of stay on the right and avoid obstacles by moving a little bit to the right. So our three other charts are simply density charts of the distribution of the data. So this one is represent the whole data, and two charts in the bottom represent the half of the data each. So the left one represents data with negative initial state, so when we already start a little bit on the left, and this chart represents positive initial state when we already start a little bit on the right. So I plot the same chart for the test data, and it looks more or less the same. It's more noisy because it has 10 times less data, but the idea is absolutely the same, and the distribution is completely the same. It's generated using the same logic. So this is it for introduction. Let's actually go to the real modeling and see how different model models deal with this problem. Again, so we have in our training data, we have very simple data set. We have initial state, and we have the action that were taken by someone controlling the robot. So let's do the obvious things. Let's try to train machine learning model to predict X given S as an input. So as a first example, I want to train the model using mean square error loss and regression problem. So ideally, whenever you train any machine learning model, you should choose laws that aligned with your final objective that you want to optimize. And in our case, we want to optimize our success rate. And it's very, very unclear what is the loss function that actually optimizes our success rate. So as a first attempt, let's try to use the most common and the most default loss, mean squared error loss. So here I trained a simple model. So again, as an input, I use our S. As an output that I want to predict, I use the X from our data. Then I create the PyTorch dataset and data loader. And then I use very simple model that I want to train. And this is multilayer perceptron. So it's basically, I use two hidden dimensions of size 32 each. And it is simply applying 3 linear layers to the input with some ReLU and dropout between them. Again, it's the most straightforward neural network that you can make, and it's pretty small. And I will use the same model across all the different approaches in this video in the future. Also, I wrote this simple function that is training model for one epoch. And it's very straightforward, very default way to train PyTorch models. So I will not really stop here because it's very default way to train the model. And okay, let's just train it. So again, I define optimizer, MSE Loss, and so on. Nothing specific for this. Again, it's very default way how you train models in PyTorch, and then train it for 100 epochs. It takes a few seconds, and we will soon get the result. Yeah, you can see that we trained the model that looks like this. It's linear layer, ReLU activation, dropout, another linear layer, another ReLU and dropout, and finally the last linear layer that has one output feature. Now let's make the predictions. Again, everything's very straightforward. We take test data, we take all the S from test data and send them inside the model to get our predictions. And then we can see the predictions here for the first 10 data points. And we already can see that the success rate of this model will be very low, because as we remember, we successful if the absolute value of prediction is above 1. And we can see only 2 numbers that are higher than 1, the absolute value higher than 1. And in 80% of cases, we actually fail. Let's just compute the success rate strictly, and it's just 22%. So our model is really pretty bad for this very simple, straightforward task. We cannot really make the correct predictions. We cannot get the high success rate. So now let's look at the distribution of the predictions, and let's try to understand what's happening. And if we plot our predictions using this orange color on top of the blue actuals, we can see what's happening. Our model predicts actually reasonable predictions on the left side and on the right side. And this is the areas where our problem actually converges to unimodal distribution, because we don't have any points here, all the points concentrated here. So it's like simple unimodal distribution, and this MSE loss based regression is pretty good at predicting reasonable numbers. And the same happens here, but everything in between is bad. Everything in between is kind of close to linear function that instead of choosing one mode, instead of choosing whether to go to the right or go to the left, is actually averaging these two options and predict something in between. That results in our robot actually hitting the obstacle and fail in the task. You can also look at the distributions, but they're not very interesting here because we know that our model completely failed to predict what we wanted from this model. And now let's try to understand why it's happening. So if you look at MSE loss, let's say you have some set of numbers 1 to xn, and you want to have like some prediction p that minimizes the mean square loss for this set of numbers, so minimizes this function. Then the optimal p that minimizes it equals mean of this x, equals average value of x. It's a very important concept, and it's I think very well known, and it's very easy to prove from this formula that this one is the value that minimizing this loss. So if you don't understand why it's happening, I think it's a good time to actually try to prove it yourself. It's very good and useful exercise, because it's this fact that MSE is optimized at the mean of the values that you have in the data set is very important and like used everywhere. So yeah, just take a couple of minutes and try to prove it yourself if you don't know how to prove it, because yeah, it's very important. But for now, let's just assume that it's true. So it means that for every initial state, for every state that we have, our model will try to predict expected mean of the data points in the training data set. So it will take points over here, points here, and return some expected mean value for these points. And this is definitely not what we want from our model. Let's try to add some visualization. So in this chart, I plot the distribution of the data that we have in training, and I compute the mean value for the whole data. And you can see that when our distribution is symmetric, then we basically predict the middle of the distribution. We predict the 0, and in practice it means that our robot just directly faces the obstacle. And the problem is that even when we filter out the data where that has one mode that is dominating another, we will still see the same problem. So here, what I did, I filtered out data with initial position between 0.6 to 0.7. It means that originally our robot is already quite far on the right. And I plot the same chart, and you can see that, yes, our mean shifted much closer to this like right mode, right part of the data, but it's still in the middle. It's still kind of less than 1, and it still will be fail for our case. And it's happening because the impact of this small mode is still very, very strong. You may know that MSE loss is very sensitive to the outliers, simply because we use the like squared distance from our prediction to the actual data, and you can consider this second mode as an outlier. And the impact of this like few data points that are on the left is so big that it's overcoming the impact of this big mode that is very close to this mean. So it means that even if there is like just a few samples on the left, they will pull us to the left, they will pull mean so much to the left that we will fail in avoiding the obstacle. And it's definitely not what we want. The question is, okay, so if mean is not what we want, and optimizing for the mean is always leads us to the bad predictions, can we switch to something else? Let's say, can we switch to the median? Will it be better? So let's try to look at it. And the answer is yes. So if you look at the median, if you plot additionally median to this chart, then this median is actually very close to the middle of the this dominating mode. And this is what we want. And you can understand why it's happening if you remember the definition of median. So median is such a point that 50% of data is less than this point, and the 50% of data is higher than this point. So it means that even if we have little bit unbalanced two groups of data, so one on the left, one on the right, and we know that, let's say, group on the right has little bit more elements there, it means that median should belong to this group, because the point that because this group has like more than 50% of the data, and it means that that point that is exactly in the middle will definitely be in this group. So we can see that when our data is, when we look at the skewed data, then median sticks to the dominating mode. This is exactly what we want to have. But let's look at the case when the data is actually very balanced. So let's look at the whole data distribution. And we can see that even now median works, because most probably we have like few elements more in the left side of our distribution, and even so our mean is very close to 0. Our median actually sticks to one of the modes. So it means that this mode is like slightly bigger. The kind of group of this cluster of actions is slightly bigger than this cluster. And our mode sticks to this cluster and predicts a reasonable value that allows us to avoid the collision. So it seems that if we switch our model from optimizing for the mean to optimizing for the median, some expected median, then it should work and it should improve results a lot. The question is how to do it. And again, there is existing answer that is like, again, well-known fact. And if you don't understand it, please try to prove it yourself. Very, very, very easy proof. And it's a very important concept. And the thing is that if we replace our loss and instead of optimizing for MSE, start to optimize for mean absolute error, MAE, then the best prediction for optimizing MAE of some set of values is median of these values. So this value is always minimized when p equals median of all x's. And using this fact, we can adjust our training process, such as our predictions will be much better for our particular problem. Let's test it. So we have a theory that if we replace loss with MAE, it will work much better. So the only thing that I do here, I change loss to L1 loss, and L1 is just the different name for MAE. So L1 and MAE is the same, and L2 is the same as MSE. So whenever you see them, you can use them interchangeably. So okay, let's just train absolutely the same model with the same data, with the same training process, but using MAE loss. And then let's look at the predictions. You can see that model is exactly the same. It has the same architecture. And now we can look at predictions. And actually 8 out of 10 have higher than 1 absolute value. It means that this model seems to be much better. So let's compute the true success rate. And success rate is 81%. So it's like way, way better than 20% that we've seen for MSE loss. And we managed to achieve it by just doing a small adjustment in the data. Let's look how the predictions are distributed. You can see that in the areas where one of the modes significantly, one of the like clusters of the actions significantly dominate in another one, when we move more than, I don't know, 0.2 on the right, the like right mode starting to dominate, and our model predicts values close to this mode, predicts values higher than 1 without any problems, and the same happens when we move to the left. The only problematic area is in the middle, and yeah, you can see that on this chart I show you that even when there is very small difference, the actual median of the data will be good enough, so it will be outside of this collision interval in our use case. But in practice, model is not really predicting median, model trying to predict some expected median of the data, and probably what's happening here, because of this randomness in the generation, when you select different subsets of data, sometimes one side is winning, sometimes another side is dominating. So the model tries to smooth this transition and predict something like this in between of two modes. If you want, you can play with numbers, you can play with training logic, you can play with size of the neural network, and you can significantly improve this result. So these results can be improved up to like 95% success rate or even higher by just adjusting the model. Again, this is not the goal of this exercise. I don't want to like achieve 100% success rate. I just want to show that some approaches significantly improve the success rate overall. If you want to understand it better, try to play with the model, try to achieve much better results than 81%. It's definitely possible. I managed to do it. And yeah, so this is how it works. So simple replacement of the loss function from MSE to MAE moves us from like 20% to 80% success rate. That is great. And the good thing about it is that it's not only like theoretical exercise, it's really worked on practice. For example, if you read the paper where the action chunking transformer was introduced, they mentioned that they tried using both MAE and MSE losses, and the MAE resulted in better policies. So they see the same observation. Again, I'm not sure if it's related exactly to the multimodality, but I think this is one of the factors that made MAE loss to win. And the same observation I made when I developed my dot policy. So I recently developed a policy that shows the state-of-the-art results on some simulated data sets, including push-T that has this short-term multimodality. And I have the same observations. So I tried to use different losses, and MAE loss resulted in the highest success rate, and it wins comparing to MSE by a lot. So if you just take my policy and replace loss from MAE to MSE, you'll get much worse results immediately. So this is actually the thing that works on the actual problems when you train bigger models and try to solve some actual robotic problems. So let's, before we go forward, let's kind of ask ourselves a reasonable question. So if you manage to get such a good improvement by moving from MSE to MAE, maybe we can have some other improvement. Maybe we can replace loss with something else and get even better boost for our performance. And so is it possible or not? And the answer is most probably not, but you can try. So look at this function. So all of them theoretically can be used as losses. So this one is represent MSE, this one represent MAE. The thing is that the quality of good loss is that the loss should punish big mistakes more than like small mistakes, and ideally the farther you are from the optimal point, the higher this loss should become. And this is how you eventually converge during the training. So if your original guess is very far from the optimal point, you will get like very big gradient and will very fast move towards this optimal point. And this is how X square or like MSE works. And in other words, your function that you use as a loss should be convex. And the problem is that MAE uses this absolute value as a function, and the linear function is the kind of most concave out of all the convex functions. And if you want our loss to be mod seeking, then what we want from this loss is actually, instead of having very significant impact from the cases where we make big mistake, we want to completely ignore them. So kind of good loss as MSE supposed to give very significant impact to these outliers. But the mod seeking loss should completely ignore them. So, you know, like you see, like the qualities that make the loss very good are the qualities that make them less mod seeking, and vice versa. So they kind of have this opposite like qualities. So if you want to make loss more like mod seeking, you will make it worse in terms of being loss overall. And the MAE is kind of the best balance that we can achieve, because it's still good for overall conversions and it's pretty mod seeking. So you can use all these other functions that you can see they either completely ignore all the errors beyond some range, or like here, or they just the impact of these points getting like lower and lower. But again, the problem is these losses that sometimes they will not converge at all. So one thing that you can do, you can actually train model in two stages. In the first stage, for example, use MSE, and then you will converge to this like incorrect value in between, but not very far from the dominating mode, and then switch to some of these fancy losses that will completely ignore this part and converge probably to some mean or median of one of the clusters of the actions. So this one can work, but again, it requires a lot of tricks during the training process. You can try it. I tried this stuff in the dot policy initially and even had some short-term wins, but eventually, after I implemented all other features of my policy, I realized that MAE loss work just as well. So I just removed all this complexity with these strange losses. So again, answering the original question, you can try to use some strange losses to converge closer to the modes, but probably it will be hard. It will have some computational problems, some conversion problems, and you need to implement different tricks to make it work. So that's it about changing the loss. Switching to MAE loss was pretty good, but are there other approaches that can lead us to the good results, to the high success rate? Of course there are, and one of them is tokenization and classification. I told you that classic regression machine learning problems assume that we have unimodal distribution. But it's not true for classification. So whenever you solve classification problem, you already assume that there are like multiple classes, and you need to choose one of these classes. You never choose the like average of two classes. You choose like either one or another. And this is exactly what we want. So the classification problems are good in dealing with multimodality because by design they stick to only one of the options. So if we can change our model and go from regression to classification, then the problem will be solved. And in our case, it's very easy to switch to classification because we know that half of the data has positive action, half has negative action, and this is very easy way to cluster this data. In practice, of course, you need more complicated ways. You don't really have, you have like multi-dimensional actions. You don't have them so simply easily separated, so you probably need to train some clustering model or train some tokenization on top of your action to convert them from continuous values to separate classes. And there are different ways. For example, the BET or VQBET policies do it. And but in our case, again, it's very easy, so I will not run any clustering algorithm. It just doesn't make sense. I will simply use the like left side as one cluster and the right side as another cluster. And I will use the same model with the same parameters, but I will train it as classification model, and it will just simply predict the side of the target, so whether our x is positive or negative. Let's train this model. Again, it will take like 5-6 seconds. And then after this, I compute the mean value of data on the left and mean value of data on the right. And I will use these mean values as a prediction for our classes. So if we predict that we should go to the left, we will just use the mean value of all everything on the left. If we predict that we need to go to the right, we will use the mean value of everything on the right. So it's minus 119 and plus 120, more or less. So yeah, let's look at predictions, and we can see that all of them are correct. It means, so it's kind of obvious that in this case, in our simple example, we will get 100% success rate because our predictions have only two options, and both these options kind of lead to success. So yeah, if we compute success rate, it will be 100%. So let's plot our predictions, and we can see exactly what we expected. So we can see that when model believes that we need to go to the right, we simply predict like 1.2 as our action. When model thinks that it's better to go to the left, we simply predict minus 1.2. And that's it. So there are only two values that we are predicting. The rest of the chart are a little bit incorrect because when I plot them, I do some like smoothing. You cannot really plot the density distribution when you have only two values that you predict. So they're always just all the probabilities are concentrated in just 2 points. So it's not really plottable. So it uses some smoothing. And yeah, so you can see that this approach leads us to very high success rate. And this simple example is it's 100%. Of course, it's not 100% in real life examples. And it's much more complicated to do tokenization and clustering of the actions in real life examples. But still, it works pretty well. And there are some good approaches as VQBet that solve this problem using this kind of clusterization and classification model. The main problem of this approach is that we completely lose diversity of actions. So again, instead of this kind of diverse group of actions here and here, we predict only like 2 possible actions. That can be a problem sometimes because our robot in this case will behave too much like robot. So it's not really producing human behavior. It's more like making just one particular step all the time. And sometimes it's bad when you need high precision of the actions. For example, you kind of, let's say you have only 100 classes of actions that you get in your clustering, but in practice you need to complete very high precision stuff, and 100 classes is just not enough to be so precise. To solve it, you can create extra model that predicts, after classification model predicted, that predicts extra correction for the steps. So you can predict like one model for going to the left, one model for going to the right, that may use the normal MSE loss or whatever, and predicts extra correction to your action. So instead of just using means, you can use this more precise step. And again, this is what used in VQBet, and they managed to achieve very good results with this approach. So again, as an exercise, you can try to do it. So you can try to replace this mean values with some prediction of extra models and see how it works. You can even add this extra model predictions inside the same neural network and train them in one go, but again, it's up to you. One simple and easy way to add a little bit more diversity to the actions is do some probability sampling of the next action. So think about it. So how, let's say, LLMs, ChatGPT, return you an answer. So if you ask the same question many times, you will get different results from LLMs every time. It happens because when LLM makes predictions, it predicts probability of the next token. For simplicity, we can say next word. And instead of always returning the top probability one, it makes a sampling. So it like sample one proportional to the predicted probability. So sometimes it predicts, most often it predicts the most highest probability token, but sometimes it predicts second one, sometimes third one, and so on. So this one helps to generate more diverse responses. And we can use the same logic here, and we can try to generate more diverse actions. So for example, if at this point, somewhere here, we predict around like, let's say 55% to go to the right, 45% to go to the left. Now we just stick to this choice and always say to go to the right. But let's change it, and let's in 55% of cases predict to go to the right, in 45 predict to go to the left. And I did it below. You don't need to retrain the model, you just need to change the way how you make predictions. And it will look like this. So you can see, if you look at this data, that we now, instead of having like this point where we completely switch from going to the left to going to the right, now we have like smooth transition, and we sometimes go to the left here, sometimes go to the right here, sometimes go to the left here. And the actions of our robot will be more diverse, more like human-like. Maybe it's not very visible in this case when we have only 2 clusters, but if you have like hundreds clusters, then it will be more visible, and we will see that robot is acting less deterministic. Yeah, so this is what I wanted to say about these approaches. But again, the problem is that if you want to completely reproduce human actions and completely reproduce the distribution of the actions as it was in the training data, we need to use some other approaches. So the approaches that we mentioned so far, they don't solve this problem. And to do it, we can use diffusion policy. So diffusion policy is very interesting concept because it allows us to actually model the whole distribution rather than doing point predictions. And diffusion policy initially became popular in Gen AI, in image generation area. This is why I think it's easy to explain how diffusion policy works on the example of images. So when you train diffusion model, you do the following. So first of all, you have some data set of images that are similar to the images that you want eventually generate. So let's say you want to generate like images of my robot. So then you do what's called the forward process. And forward process means that you take the original image, then add a little bit of noise to this image, then add a bit more noise, then add a bit more noise, and then eventually add extra noise. And at some point, your image is doesn't have anything from the original image at all. It looks like pure noise. Here I use just 4 noising steps. In practice, you use either more than tens, so it's usually, I don't know, from 50 to 1,000 noising steps that you really apply to the image. And also in some approaches, you apply it not in the image space, but in some latent space and so on, but we will not go there now. So let's assume that we, for simplicity, apply only 4 steps here. And then you train the model. But eventually you want your model to be able to transform pure noise to the original image. But it's not exactly how you train it. When you train the model, you train it on much simpler task. You train it on the task of one-step denoising. So you train your model to take this noisy image and remove the noise from it. So given this image, generate this image without noise. Then you train the same model to denoise this image. So take this image with a lot of noise and remove some of the noise. Then you take this one where you barely see some outline of the robot and train the model to remove this noise. And then eventually you train it to take the complete noise and kind of remove a little bit of this noise, such as you can see the outline. So again, when you train the model, you train it to do one denoising step. So you train it to go from any image here to the next image on the left. So your model is, after this training, is capable of removing a little bit of noise by moving towards the image of the robot. And when this model is trained, on the big amount of training images, you can do the following. You can generate completely new, completely random noise, and then ask your model to denoise it by one step, and then ask to denoise it one more step, and then ask to denoise it one more step. And eventually, after the same number of steps that you use for training, it will generate the image that, if model trained correctly, will resemble the real image of the robot. So again, when you do the training, you just take the existing image in multiple small steps, add more noise to it, then train the model to remove a little bit of this noise one step at a time, and then just apply this model to the completely random noise, and this model eventually managed to generate the real image. Of course, in practice, there are a lot of kind of complications. You need to add this noise in a specific way. We need to train the model specifically, and there are a lot of technical details. But the idea is as simple as this. And eventually it means that your model, with all this noise in the noising process, learns to transform any random noise into some reasonable image. Here you can ask the question, so we don't generate images, yes? So in robotics, we don't need images, we need actions. So how can it be applied to robotics? And the idea is that it doesn't matter what you generate. So if you train your model on images and learn model to transform noise to images, you will generate images. But if you need to generate new actions, you just train your model on actions. So you take original actions that were made by human add some noise, add more noise, until it becomes complete noise. And then your model will learn to transform complete noise into reasonable actions. So in our case, it will learn to transform random normal noise into the reasonable action distribution that we have in our training data. And this is as simple as this. So instead of this very complex data structure as images, we use our actions, and the model still works fine. This approach still generates very, very good results and manage us to generate the actions from the same distribution as in the original training data set. As I said, the reality is a bit more complicated because you need to add this noise in some particular way. You cannot just add it completely randomly and so on. So for the illustration, I used probably the simplest way possible of adding the noise, but still it required to write some formulas and some not very straightforward code. I will briefly go through it, but I encourage you to actually read through it and try to understand code yourself here. So yeah, the idea is following. So the noise adding logic looks like this. So xt minus 1 is some signal, some noisy signal at step t minus 1. And then we want to add extra noise to get the noisy signal at step t. So we do it using following logic. So first of all, we multiply it by square root of at, where at just shows how much variance of the signal kind of stays there after this extra noise in step. And then we add extra noise multiplied by square root of 1 minus at. Again, I will not go very deep into these formulas, but if you add noise every step by this formula, you can also estimate how your noisy signal at step t will look like given your original signal without noise and given the noise that you're adding. And it will be described by this formula. But again, I will not go into details. You can read about it afterwards. So to simulate it, in this simulation, I use 49 diffusion steps. So it's like 49 steps of adding or like removing noise. It's 49 because it's nice to plot in the end. If we add the original noise plus 49 step, we'll get like 50 of them, and it nicely fits into the grid. So this is the only reason why I use 49. But it's kind of enough, more than enough for this particular problem. Then I generate BT and AT that are simply the noise in schedule, and this AT represent how much of the signal variance we preserve at each step. And then when we compound all of them, we can see how much of the original signal, of the variance of original signal stays there after each step. So when we just start, after the first noise in step, we add just a little bit of noise and almost all signal is still there. So our signal is just slightly noisy. But after 49 steps, only 0.005 of the original signal variance will be in our signal noise. So at the last step, that is similar to this one, we will have 0.5% of the original signal. So it's not really going to zero completely. It will be 0.5% of the original signal and 99.5% of complete noise. So this is how our noise and schedule work. And then I going to train the model. I use the same model, but now it uses 3 inputs. I will talk about it in a second. I use MSE Loss. So in this case, we can use MSE Loss. We shouldn't use MAE. If you use any other loss, you will kind of break a lot of things in the logic, and it probably will not work. So make sure that you use MSE Loss. And then what I'm doing during training, I generate random step for each sample in my data. I generate random noise for each sample in my training data. Then using this formula that I describe here, I compute, for each sample, I compute the noisy version of this signal after random step t that I just generate. And then as an input for the model, I use the original state of the robot as before. Then I send to the model the actual step. What is the noising step that we are at right now for the sample, and I send the noisy signal at this step. And the target of the model is the noise. So in practice, kind of, let's say, if you were doing it with images, I would send like this image, set that is second noising step, and I will try to predict the noise that was added to this image comparing to the original signal. So this is what the model is trying to predict. And yeah, like I'm doing it slightly weirdly because I redefined train data set and train data loader for each epoch. So in practice, you probably should do it a little bit differently. It's not the optimal way, but this way just allows me to write down the main diffusion logic in one place. That is much more convenient. So let's train the model. Again, 100 epochs, same model, but now it's predicting different things. And now our model learned to predict noise. Yes, so if we pass the original state, a step, and the like noisy signal to the model, our model can predict what is the noise that was added to this to the signal to get this noisy signal. Then we somehow need to do the denoising process. So we somehow need to go from this noisy images to the original images. So in our case, from noisy complete noise to our reasonable actions. And this is pretty complicated step. There are different ways. You may hear about the DPM or the DIM, and it's different abbreviation that describe the denoising processes that can be applied. Here I show how to use the DIM with eta equals 0. I think it's the easiest and most straightforward way in terms of the actual formulas. So you just take the formula here that I used before to generate training data, and using only this formula, you kind of can get the formula that shows how you should adjust your noisy sample to make it a little bit less noisy. So we need to subtract this amount of noise that you predicted and then scale the signal a little bit up. Again, it's not very obvious. You probably need to go through the formulas. I would recommend you to read more papers about diffusion and how it works and try other types of denoising approaches. But yeah, trust me for now that this formula works. And here I simply apply this formula. And instead of just making predictions once, I actually iterate 49 times and make predictions 49 times step by step, each time denoising the original noise by a little bit to generate our final predictions. And you can see that they are kind of good. So we see first 10 predictions, all of them are actually successful. And we can see that there is some variance, so we are not predicting some flat values. So let's look at the success rate. Success rate is 95%. That is pretty high. And let's look at our distributions. And you can see that even so, again, you can see that it's not ideal, actually, but the distribution of predictions is much closer to the original distribution of the data than in any previous approach. You see, again, it's not exact match. We see there is like some extra variance. There are some samples that go into area between -1 and 1, so we are like far from ideal. But the actual distribution, the orange one, is very close to the blue one. You can, and the works when we look at partial data, when we condition it by the value of initial state, we can see that our distribution that we managed to generate is much closer to the distribution of original data. It means that if you apply the same approach to the robot, the real robot, in the real environment, this robot will not converge to one action. It will really do like different actions, and the behavior of the robot will really resemble the behavior of the human. That in many cases is very useful, and this is what we want to achieve. So again, it's not ideal. You can see higher variance. You can see, for example, here that we have predictions while we shouldn't have them at all, and so on. but again, we get like very good success rate, and we get very results that are pretty close to the original one. And again, you can play with parameters, you can play with the denoising strategy, you can read like some papers about it, you can try to implement other denoising strategies. I managed to get success rate higher than 80 or 98%. So you probably can get even higher if you again play with like model training and the denoising approach. There are different ways how to improve it. And finally, let's plot the evolution of distribution. So as I said, I make predictions of the model like 49 times, and I actually saved all these predictions after every step in the predictions list. And here I plot the distribution of this prediction. So at step 0, we have our original noise. So this is just data generated using random noise. So for each sample in test set, I generated simply random noise. And then I started denoising it step by step. And you can see that in the first like 30 steps, nothing changing much. But somewhere here, after step 33, 34, we can see that there are two modes in this distribution now. And they're starting to shift farther and farther away from each other. We are like removing more and more noise at each step, and eventually we end up with this distribution that again looks very close to what we have seen in the original distribution in the training data. So this is what we wanted to achieve, and this is how it works. Like step by step, we start from complete noise, and then step by step we remove noise from the noise, and then we have only the signal left, and this signal really resembles what we had in the original training data. Okay, diffusion let us achieve our results, and actually diffusion is very popular policy in robotics. So original diffusion policy became sort of in imitation learning when it was released, and now many state-of-the-art models with especially like VLA models, they use diffusion as the last stage of the model predictions, and it's becoming the industry practice. So yeah, it's the like one of the state-of-the-art approaches that many policies use nowadays. But there is another approach that called flow matching that actually doing very similar things and recently replacing diffusion in many places, starting from image generation, and now it's applied in robotics too. One interesting thing about flow matching, so if you look at the original papers about diffusion models and about flow matching, they look like kind of papers from different areas of math. So they use like different logic, they use different terminology. For example, diffusion policy talks about this like noising, denoising, forward processes, and so on. Flow matching talks about some vector fields and differential equations and so on. And you read it, and they kind of really very different papers. They don't look like they're talking about the same stuff. But in practice, they're actually talking about the same stuff. And they this diffusion and flow matching is kind of the same approach. It's the same idea, but just authors of these two approaches just came to the same idea from two different sides. So they actually converged into the same logic, but from like two different initial positions. So it's very cool, but again, it can be pretty confusing when you start reading especially old papers about this. When you read like more recent papers, they're usually described in more like similar way, but yeah, the original one using different language. Maybe for simplicity, I can give you this analogy that is not strictly correct, but I think it helps to understand the difference between diffusion and flow matching. So I would say that diffusion relates to flow matching as this summation relates to this integral on the right. So if we ignore the like some edge cases of strange function, and if we choose pretty high n, then this summation of like few discrete numbers is approximately equal to this integral. And the same with diffusion and flow matching. So diffusion is a process where we add some noise in some discrete steps a few times. And flow matching is very similar concept, but we are moving between the complete noise and the signal in using some continuous process. So instead of adding like 50 steps, we just continuously move from one point to another. Again, it's not ideal analogy, but I think it can help you to understand how it works. And again, so let's say in diffusion case, if we have some noise like this, then we apply like a few discrete steps, and in these steps we generate the final image. But in flow matching, we kind of apply the continuous process that smoothly transforms from the complete noise into the final image. And this is the main difference. So the rest is kind of similar. The nice thing about flow matching and why people actually like it is because it's much simpler. So remember, for this diffusion, I said there are like some complicated formulas and so on, and we need to define this noising schedule pretty in some particular way, otherwise it will not work and so on. But with diffusion, it's not the problem. In diffusion, the process is modeled in an extremely simple way. So we have some actual signal, we have some noise, and we simply interpolate between them using this t from 0 to 1 that is uniformly distributed from 0 to 1, and t is simply moving. When t equals 0, we have complete noise. When t equals 1, we have complete signal without any noise. And at each point in time, we use the simple model to diffusion, but instead of predicting noise, we predict difference between the signal and the noise. And that's it. The rest is actually the same. And when you go through this notebook, I actually recommend you to go through the flow matching first, because all the formulas are simpler, but they're very similar to diffusion. So if you go through these formulas first and then go to diffusion, it's probably will be easier to understand. So yeah, like I trained the model that is doing very similar stuff, but with much simpler formulas. And then the denoising process is also much simpler than this one. You don't need these big strange formulas anymore. You simply take the noise and then in n steps just add model predictions multiplied by a small number to your signal, and that's it. And this is how the denoising process works. And again, its idea is the same as in diffusion, but the formulas are much simpler. And you can see again that we get pretty good results. So out of this 10 first samples, all predictions are success predictions. The actual success rate is slightly lower. It's 94%, but again, it's just noise. But the distribution actually looks even closer than distribution of, in the case of diffusion model. You can see that we almost exactly match the distribution of the original data. We have like a bit more data here, right? Like close to the border of like success rate region. So yeah, it's probably not such a big problem in the real life. And you can see that these dots are much more aligned with the blue dots. So we actually managed to reproduce the distribution very closely. And here it's the same. So when we look at some conditioned distribution with negative and positive initial state, we can also see that we match the original distribution very well. And let's also look at the plot the evolution of distributions. Again, we start from some random noise and then apply it again and again. And much faster, after around like 26 steps, we already see two modes in this distribution. And then we finally split them into like two nice separate distribution for the going to the left and going to the right. So yeah, this is how flow matching works. Again, it's hard to explain everything in just a video, so I definitely recommend you to go through this notebook to look at the training process, look how exactly it's done, and it will be very good exercise for you to understand how the things works. Because in practice, in the like real robotics models, they are applied more or less in the same way. So yeah, the models that I used are more complicated and so on, but the general idea is very similar. And if you want to learn and like use diffusion and flow matching in your models, please like try to understand and go ahead. And I'd recommend just go for flow matching directly. I don't really recommend you to go for diffusion, because I think a lot of VLA models currently switching to flow matching. I know, for example, the Pi 05 that was recently released use flow matching to generate final actions. Yeah, I think flow matching is a go-to choice right now if you want to reproduce the distribution of the your training data set. And yeah, and another things I also recommend you, if you want to look deeper into formulas behind the diffusion policy and flow matching, I recommend you to watch or at least read the MIT course about it. I will give you a link in the description, and it's a very nice course that explains everything from the stochastic differential equations standpoint. It's kind of very heavy in terms of math, but it kind of derives the most general formulas to describe both flow matching and diffusion processes, and allows you to actually, if you understand it on this level, it allows you to tweak the process and make some changes if you want. So I think it's a very nice course, and I will definitely recommend you to go through it. And yeah, so I think that's it. This is all I wanted to cover here. Just a reminder, we started from the discussion of multimodality problem. Then we defined some simple DMO problem and shown why the straightforward MSE regression fails to solve this problem using imitation learning. And then I shown that there are multiple ways to solve the multimodality. One is to use MAE regression. That is the simplest one. Then we can transform the problem into classification by tokenizing our actions. And it's also pretty often used in real applications. And finally, we can, instead of doing this, we can try to actually reproduce the whole distribution of possible actions from the training data. And to do it, we can use either diffusion policy or flow matching. So I think this is it, and it covers most of the main approaches to this problem. Thank you for watching. I hope that this video was useful for you, especially if you want to experiment with your own policies. Then all this like high-level intuition behind the multimodality can be very, very useful. Just want to remind you that here I described everything in the very, very simple toy example. In the real life, everything is much more complicated. For example, like long-term multimodality can work a little bit different, and all these approaches can have different pros and cons. Again, for example, you might think that flow matching is the best choice based on this video, but it also has some drawbacks, because to make the prediction, you need to run the model, I don't know, 50 times during the inference. That of course require much more resources and make your model slower. So again, it has all of them have like some problems and some benefits. So whenever you develop your policy, you need to weigh them. But again, I hope it was useful. And please, if you have any questions or comments or anything, leave them in the comments below this video. Also, like and subscribe if you want to see more video about robotics. And let me know if this like theoretical video is even interesting, or should I just post more video with actual robot demos and so on. So yeah, let me know, and see you in the next video. Bye.